in small deflection assumption, we said that any kind of deflection here we use theta, sometimes we use delta, or sometimes we use x. And it makes no difference when we apply the small deflection assumption. Doesn't matter what variable you use. But the point is, first, we were going to say that because theta, in this case theta, is much less than 1. It's not much less than 0, but it's much less than 1. So we can say that sine theta will approximate it to what? When theta is very small, sine theta is very close to theta. Would you agree?
Yes.
Right? And cosine theta, on the other hand, cosine theta will approximate to 1. And from now on, whenever I talk about small deflection assumption, I basically means this. We're going to replace everything. Sine theta, we're going to replace sine theta with theta. And we will replace cosine theta with unity. Now with these two, of course, you know that what happens to tangent theta? What would tangent theta be approximated to?
Theta.
Yes, theta, right? Now, after applying this assumption, we have this result. So P can be approximated to this. Ks times theta, L times theta will approximate it to, this will be approximated to theta, which is this one here. And then this 2 theta will cancel out, right? So in this case, the critical load will be approximated to Ks over L. This is the critical load for the problem. But keep in mind that only approximated to, because we let sine theta to be approximated to theta. This is what we call the force approach. Now, in force approach, there are 2 main steps you will need to remember. One is always to take free body diagram. Once you have established the free body diagram, the next step is to take the moment equilibrium, these 2. That's the 2 key steps in the force approach. And the next approach I'd like to show you with exactly the same problem is what we call energy approach. If we use the energy approach, we will not take any force equilibrium. We will not need to establish any free body diagram. Instead, we will calculate just the energy terms. And we're going to calculate the strain energy, external work, and the total potential energy. So the first thing we need is to find out what is the strain energy. In this case, there is a rotational spring. So the strain energy denoted by capital U equals to 1/2 of the times the spring constant, rotational spring constant Ks, times the angle of rotation square. So it's going to be Ks times theta square divided by 2. That would be the value of strain energy of the system. External work. Denoted by capital V. So how do we calculate work? If you remember, but this of course, for many of you, this has been some time ago. work equals to what? Equals to the integral of force vector, the dot product with the corresponding deflection. That's what we know from dynamics. I believe that's the first time you've been introduced the concept of work. So that's by definition. And in this case, all you need to do is to find out what is the force and how far does the force travel in the direction of the force. So in this case, here, how do we know the direction of traveling? And you may want to use this triangle to help you to understand. And in this triangle, we have this beam, right? That's what is column. And once it's rotated by the angle theta, we know that the total length is from here to here. This is L. This is theta. Now the force is applied at here. So how far does the force travel? The distance in which the force travels is actually from here to here. Would you agree? Right? That's how far does the force travels. The force eventually will move to be here. That's how far it travels. So the question becomes, what is this distance? What's this? And it turns out that this distance is just P times L times 1 minus cosine theta. Would you agree? Actually, the distance is not. The distance is, there's no P here. Distance is just L times 1 minus cosine theta. Would you agree? Right? Okay.
Yeah.
Therefore, what is the total work? Total work in this case is just force times the corresponding traveling distance. Therefore, capital V is just P times L times 1 minus cosine theta. That's total work. I'm sorry, that's external work. And next, we're going to introduce the concept of total potential energy. So what's total potential energy? Total potential energy is denoted by capital Pi, equals to capital U minus capital V. So it's basically the difference between strain energy and external work. That's just by definition. Now, that means in this problem, of course, that's why I have to use the example to introduce the concept of the energy approach, because when I introduce the strain energy, I need to give you some expression. That's why I use the example to do this. And in energy approach, we have, I need to go to the next page, which is page 13.
Can you go
In energy
Professor,
approach.
Professor, would you mind just going back just for 1 second? I just need to finish writing down that last equation.
Yep.
Ah, okay, thank you.
Yep. In energy approach, when the change of strain energy, the unit change, we're going to use delta here, just to show that this is the unit change. And delta U means the unit change, slight increment of strain energy. When the change in the strain energy is greater than the change in external work, which is delta capital V. When that's the case, we call this kind of system stable. When it's otherwise, capital U, delta capital U is less than delta capital V, we call the system unstable. And when the change of strain energy equals to the change of external work, this is the case or the condition we use to determine critical load. When this is true, the corresponding force equals to the critical force or the critical load. So this is how you're gonna use to determine buckling force by using this condition. But furthermore, there's more the energy approach can tell us, such as when the derivative of the total potential energy with respect to variable, in here we use theta, so we're going to say d capital pi d theta. When this derivative is 0, we call it equilibrium condition. But this information, it does not indicate just the structure's condition at buckling, but it's actually for post-buckling. When the second order derivative of the total potential energy with respect to the variable, in this case is theta. In other cases, it could be x, or could be other variables, or could be y. When this ratio is greater than 0, we call it stable. But this is not at buckling, but we call it stable post-buckling. And of course, I made a mistake here. If you notice, there's no x, right? What's this one here? This should be theta, because we use theta in this problem. And if otherwise, the second order derivative of the total potential energy is less than 0, we call it unstable post-buckling.